So I'm going to talk about, oh, it's not working properly, right? I think it's not. There is a problem of resolution. Okay, now it's fine. Sorry for that. Okay. So first of all, thanks for the organizers for inviting me. My talk is a little bit different. It's very specific. I'm going to talk about rumor models on hypergraphs. The idea here is to discuss how to model how information and more specifically how rumors or gossips travel in a group kind of system, basically a hypergraph. Our main motivation is our systems like Telegram or WhatsApp, where we have groups of people interacting, so sending messages in groups, which is different from sending messages in pairs, and how this will change the dynamic itself. The first rumor model was proposed, I think, if I took the note correctly, in '65 by Daly Kendall, and they realized that information and disease, they spread more or less the same, but their idea is that in a disease, when you get the disease, your immune system start working, and it's a process that depends only on yourself. While in a information or rumor, what happens is that you lose interest on the information when you try to spread the information to someone that already knows this piece of information. So the difference is in the disease, the information is you lose interest or your immune system works, and then you heal by yourself. So an individual process, while on the rumor, we have a contact with someone else to annihilate the process itself. So the questions I'm going to try to discuss here are these ones. It's how does this compare with a pairwise case, and what kind of behaviors should we expect, and what are the differences between the pairwise and the higher order behavior. And finally, I would like to try a little bit to answer this question of, can we validate, is this a better model than the pairwise? So first of all, I want to introduce the classical model, the model by Mackie Thompson, which is a slightly different from the Daly-Kendall model that I presented before. Here, the contacts are directed, while on the Daly-Kendall model, the contacts are undirected. So basically, on this process, we have three classes of individuals. We have ignorants. There are people that do not know the rumor, and they can learn it. We have spreaders. There are people that know the rumor and are trying to spread it. And we have stiflers. That are people that know the rumor, but they don't want to spread it anymore. Mathematically, what we do is to associate to each individual in our dynamics three random variables, three Bernoulli random variables, which are x, y, and z, and they are mutually exclusive. And we set a 1 to define the class we are in, the individual is in. So this model is composed of two mechanisms. The first one is the contagion or the spreading. So it happens when a susceptible or an ignorant node contacts a spreader. So the spreader basically passes the information. So we have the contact of one spreader node with an ignorant and a spreader, and then we have the pass of this information. So the same way as we have in a disease. And then the second mechanism that we have is the annihilation, which is similar to the recovery on the epidemics case. And here is the difference. We have the contact between a spreader and someone that already knows the information, which is basically a spreader or another stifler. So the idea is I tell this information to someone, this person already knows this information, and then I say, okay, this is not fresh news anymore. So I don't want to spread this anymore. And then I turn into I stifler. So those are the basic rules that define the model. And the thing is, this works very well in pairwise, but how can we generalize this to more complex environments like the WhatsApp or the Telegram that we have groups, for example? It's not that straightforward, and that's the task that we are going to do here. So basically what we do is now I'm trying to present our own model, and the idea is that, first of all, structurally speaking, we are going to map Telegram or WhatsApp, or even like we can even think of this conference as a group itself. So the group structurally will be a hyperedge, and what we will have is a system that is a collection of hyperedges or groups, or Telegram groups, or WhatsApp groups, and so on and so forth. In terms of states, I'm going to have the same states as before, as in the classical model. And in terms of mechanisms, what I'm going to say is that the contagion, which is the first mechanism that I mentioned, it will be given by a critical mass process. So when we have one information going on a given Telegram group, for example, when we reach a critical mass of spreaders, we will say that the whole group is active, and I will activate everyone that is inside this group. So the first thing that I should do is to justify why should I use this kind of function. So why use a critical mass or a half side or an indicator function, you call as you prefer. So the idea is that in sociology, anthropology, there are many studies showing that they have what they call this tipping point kind of dynamics. So there are, for norms, this is very common, and there is this specific work that's actually motivated our choice, which is the experimental evidence of this kind of behavior. So basically, they invited a lot of people in the lab. They did an experiment showing that if you have a committed minority of around 20 and 30%, you are able to change a given norm. So basically, they do this on a computer. They invite a lot of people to the university. They implement a game, and they put a fraction of bots that doesn't change their minds. And then they show that when you have around 20 and 30% of bots, the consensus changes to something else. So we are going to use this kind of function to model the spreading of our information. So mathematically, what we do is that we associate, for each hyperedge, we associate a variable tj, which is actually the sum of active nodes inside the hyperedge. So we just count how many active hyperedges, how many active nodes we have in each hyperedge, and then the spreading process will be given by this expression here, which is basically counting how many hyperedges you have active, and then you have a contagion rate, which is lambda, but I'm not going to get into the details about the rate now because I don't want to explore this in this presentation. So we have two mechanisms, the spreading and the annihilation. So the spreading we already generalized, but how can we generalize, or how can we propose a different higher order annihilation mechanism? So the idea here is that when you're using Telegram or WhatsApp, you're going to stop not only when you try to contact someone, but when the number of groups that you participate is larger than a threshold. So what we are going to propose is to use another critical mass, but now based on the number of groups that you have. So you're going to see that you have a couple groups that are active, in this case more than half, and then you're going to say, okay, people are already talking about this, so it's not fresh news anymore, so I'm going to stop. Mathematically, we can write an expression that is like this. We basically count the product of the states. This is going to tell us if a hyperedge is active. We sum over all the hyperedges, and then we can conclude our equation, which is going to look like this. So just note that the spreading dependent on the number of hyper edges you participate, while here in the annihilation process, it depends basically on you. The critical mass is on the individual itself. So, as I said before, I wanted to focus on the thresholds instead of focusing on the rates. And what I would like to mention, I think is the most interesting result that we have, is that we can have this kind of a phase space here, in which we have a very rich and unexpected kind of behavior. So when we have a very high contagion threshold, what we have is that we have no contagion, and this is easy to see because if the contagion threshold is very high, you cannot start to propagate. And then we have this region here, which is the most interesting one, where we found continuous transitions. Here I would like to make a small parenthesis saying that we can also find discontinuous transitions, but in this presentation I'm going to focus on a specific set of parameters in which the transitions are continuous. So to be more precise, the model has both continuous and discontinuous transitions. But in this case, continuous ones. And what is different about them is that we can have a region in which the subcritical has exponential decay. So it will look like this. This is the time to get to the absorbing state. And then we can see the transition will be around the peak of this. However, we also have a region in which the time to get to the absorbing state follows some sort of power law, which in practice means that to kill an information, you have to talk about it. And finally, we also have this upper region here in which we have no transition at all, but different from this one, what we have is an always supercritical regime. So the annihilation threshold is so high that you spread to the whole network or to a good fraction of your network before you can start annihilating the process. And everything that I said is correct, but it's an homogeneous system property. When you go to heterogeneous systems, the important part is that when you start the process, the initial condition, the process is very local. So it will depend on the initial condition. So in heterogeneous systems, what you have is a mixed behavior between this exponential and power law decays. And that's what you can see here. For different initial conditions, you can find the different behaviors, heterogeneous network, different behaviors depending on initial conditions. This is the message. So, okay, we already showed that the model has a very different kind of behavior. Something that I would like to mention that I forgot is, especially here, that this kind of exponential decay, it's very similar to SIR models, while this kind of power law decay, it's a characteristic of a Mackey-Thompson model. So this might, in a way, explain why a lot of people use SIR models to model real processes, and there is this mixture of models in the literature as well. Okay, so the idea is, okay, this is the model, we have a lot of behavior, we have a lot of different things, and then we have a mixture of things in the mixture of behaviors in this model. So now we want to again try to validate this using real data. So basically what we did is to use this data set that was already on the literature. It's a Telegram data set where you have a lot of users, public groups, and you can track the message and how it moves inside the groups. So what we did is to try to analyze the cascades of how the rumors are spreading. So we got the messages, and we got only the messages that have some sort of URL. And then we use the URL as a unique identifier for the message to track it in the different groups. We create a cascade of rumor, a cascade of these messages using the times that are on the data set. We define the survival time as the last one minus the first one. And here I would like to point a problem that we might have, that we might know that we had, that is, when you stop spreading a rumor, you don't tell anyone. So the last time is not actually the last time that you transit from a spreader to a stifler. So this is kind of an approximation. And another quantity that we studied is the average inter-events time, which is basically the average of these times here. And this you can all get from the data. So with this data and with the model, what we do is basically simulate the rumor in the same structure, in the same hypergraph that we get from the data set. And then we have our model. We can collect all the intervention times, we can collect the survival times, and then we can compare data versus simulation. And this can be done like this. The kind of plots that we have look like this. We also, in the paper, we also studied the phase transition of the model using this kind of plots as well. So it's a bit, the first thing that I would like to say is that you can really see the similarities, and it's kind of working. And what I wanted to show here is that first, they kind of look the same, not very much in this region here, but this is the supercritical region. So in the simulations, you can have supercritical, but in the real data you don't have, just because you don't have. So this is why it's not matching. And the most important part is, and it's kind of difficult, but those processes, they are happening near criticality. Because if you look at this is the order parameter versus lambda, you can see those lines here that represent the same points in the phase space, and then you see that the real rumor, at least the simulated, is here, which is similar to the real rumor here. So the real rumor should be happening in the subcritical and near critical regimes. So trying to answer those questions, how does it compare with the pairwise case? Well, basically what we had to do it was to propose a new higher order annihilation mechanism. That it's important to mention that this does not recover the original Mackie-Thompson model nor the Daly-Kendall model, but we thought it was slightly better in this way, because when you are on the phone, for example, you do not check, you check how many groups are talking about something, and then you say, wow, a lot of people is talking about this. So it's kind of a process that is associated to you and not to the number of people that are inside those groups. The second point is, what kind of behavior should we expect? And we should expect mixed subcritical regimes. And by mixed, what I mean is you should have exponential decay, and you should have a parallel decay, and continuous transitions. At least in the real data, we found evidence for continuous transitions. It's important to mention, and this is kind of something that we are exploring right now, is that you can also have discontinuous transitions, but they seem to be, at least in our preliminary experiments, they seem to be present only in denser networks or in cases that are not representative of the real data. And the third question is, can we validate this with real data? And I hope that we can say yes, we can. The problem is the data does not have everything that we need to give a stronger answer. However, we can also point to some literature, because we are not the first to say that rumors spread near criticality. There are a bunch of literature on that, and our idea is just to provide our model just provides a mechanistic explanation for this kind of behavior. And with that, I thank you.
Thank you very much. Are there questions? Charo?
Hi, can you go back to the slide with the decay, please?
With the decay.
Yeah. This is Conqueror by any chance?
This is?
The software you are using to show the presentation. Is that Conqueror?
The software?
Yeah.
No, it's LaTeX. No.
So, yes, so here, my question is, two questions, like double in a sense. Can you go between the green and the blue? Can you have a transition between the two types of decay?
Here?
Yeah, like if you move in that direction, can you do that? Can you cool gene in principle simulate that? And what do you expect there? And two, are you really sure that's the power of decay? How do you know it's not a stretched exponential?
Okay, so let's go first. I'll try to answer the... Okay, I'm sure I went a little bit too fast. So let's go back to the traditional rumor model. In the traditional rumor model, what we have is, I know some piece of information. Let's suppose that I'm spreading with a very, very low spreading rate. In order to stop the process, what I have to do? I have to tell you the rumor, and then I will make another contact, and I will try to contact you again, and then I will stop. And this is a Poisson process. And this has an average of 1 over lambda. So since it has an average of 1 over lambda, I have to spread to someone first. And when we are talking about the model in the hypergraph, it's exactly the same mechanism. So the idea is that I have to activate the group, and then I stop. And so this is why it's 1 over lambda, or there are some corrections, but it will be in this way. And I mean, just to conclude, I mean, since it was fast anyway, the exponential is the case that when you start, or you start in a hyperedge, where you can already stop. So I mean, the annihilation criteria is already met with the initial condition. In that way, it's just the alpha that is playing the role, just the recovery, the annihilation that will play a role. You said move from here to here. Well, this process, like, I don't know exactly how you, like, you have infinitely many absorbing states, right? So it's not that you are in a state and you can, if you dynamically change, you have initial condition and you can, yeah. I mean, you can, but it's a different system, and in a way, you know what I mean, or because like if your dynamics is active and stable, then you are in a condition, and then you move, and then you just do something different, and then this doesn't happen here because you have infinitely many absorbing states. So what you do is that either you start here or you start here. And this is important to, I mean, it's also important to emphasize that these two things are subcritical behavior. It's not anything else. It's subcritical behavior.
Other questions?
Thank you, Guilherme, for the very nice talk. Just wanted to ask you, what would happen if you added another compartment to your modeling? So you said that it was similar to the SEER model, and what about we had like a delayed transmission of the rumor? How can you treat that under your assumptions, and how would that behave along the transitions and regimes of the model?
If I had a delay,
yeah, like let's say somebody got exposed to the rumor but didn't immediately believe in it, or like had some resistance to believe in that thing.
This is interesting. There is a model that does that, which is the K exposure model, and it was done like in a complete graph, but not even in graphs so far.
There was another question.
Hi, Guilherme. Could you go around to the real data?
Sure.
Right, the last figures. Yeah, that one. How I didn't catch it. How did you determine those diagonal curves? How did you determine that they are?
These ones. Those should be the parameters that generate those points.
So for every points in those diagonals are simulations that you run with those lambda.
Yes, yes, and then like on the transition, you can see that you have the highest variance, for example.
Okay.
It's kind of you have to rotate this a little bit. You can get an idea of that.
Because then in the transition you can have the points right on the top and then the points right
exactly.
on the bottom. Okay. No,
exactly.
Thank you.
Other questions? Well, if not, thank you very much, Guilherme.
Thank you.
So now we have the lunch break.